Jai Hind everyone. So this is the second lecture of data and signal, and it is the part of computer networks unit 1 that is related to the first layer of OSI reference model, physical layer. So data and signal. In the last lecture, we have already discussed the different types of signals and analog and digital signals. So in this lecture, we will discuss the various noises, the various types of changes in the signal that can be happened during the data transmission. If we are sending something and you are not receiving exactly the same signal, it means there are some disturbance in the signal is this. So there are various types of disturbances in signal that can be understood by attenuation, distortion and noise. Okay. So first we will discuss the attenuation, then distortion and the noise. So these three are the impairment causes: attenuation, distortion and noise. So what is attenuation? If the original signal is this, it can be transferred through any transmission media. The transmission media can be wired or wireless. This is attenuated signal. During the data transmission, the signal can lost its energy and after using some amplifier, the signal can achieve again the same frequency rate amplified. Okay. So it means if the signal lost its energy at the receiver point, it means it is attenuated signal. Mind it, the signal is not changing its shape, just what? Its high and low peaks are lower. So it means it's lost some energy in the signal. So that is attenuated. We can easily recover this particular loss of energy by using amplifier. Okay. If I am asking amplifier, it means is it amplify the signal. Signal amplifier, it means it boosted the signal. In what form? It recover the loss of energy in the signal. Another term is amplifier, and second is amplifier signal boosted analog signals, while a repeater boosted the digital signal. If the example is in the form of digital signal, the digital signal loses its energy, then we have to use repeaters to recover its power. Suppose a signal travel through a transmission medium and its power is reduced to 1/2. It means the signal lost its half of its power. Okay. So initially its power is P1 initially. Now at P2 is the receiver end. It's receive P1 divided by 2. It is receive P1 divided by 2. Okay. So in this case, the attenuation loss of energy can be calculated as 10 log 10 P2 upon P1 is equals to 10 log 10.5 P1 upon P1. Means what? What is P2? P2 is P1 upon P2. Just replacing this P2 is equals to P1 upon 2, P1 upon 2. So it is 0.5 P1 upon P. So P1 cancels. 10 log 10, 0.5. It means 10 into minus 0.3, that is minus 3 decibel. The loss of 3 decibel is equivalent to losing 1/2 of the power. So listen, 1/2 of the signal is lost, but in signal it's lost 3 decibel, which is quite higher. So it means जितना ज़्यादा energy में loss होगा, it means we are losing the decibel, the power of signals. Okay. So attenuation, यानी कि loss of power, it should be not more than its some value, its threshold. Otherwise, the receiver is not able to recover its power, or receiver not able to receive the signal. a signal through an amplifier and its power is increased 10 times. So, this is the case where the power is reduced, and this is the case where the power is increased 10 times. Keep in mind, this is the case where power is reduced half. This is the case where power has been increased 10 times. Then the P2 is 10 P1. The power at the receiver end is 10 times of power sent by the sender. So, in this case, the amplification, the power is 10 log 10 P2 upon P1. It means 10 log 10, 10 P1 upon P1. It means 10 decibel. समझा आपने क्या हुआ? When the power loses its energy. So, it means when losses half power, in decibel we can say 3 decibel. When the increase is 10 times, then 10 decibel increase. It means the disturbance in signal, gain of power, we can reduce it very easily. But if the high power is lost, then it is not easy to recover it. Okay. So, one reason that engineer use decibel to measure. Why we are using this particular power we are measuring in decimal? So, there is one reason that the change in the strength of signal is that decibel number can be added or subtracted when we are measuring several points instead of just 2. So, in next figure, in this figure, we can say that signal travel from point 1 to point 4. In this case, the decibel value can be calculated in this way: -7 plus 7 minus 3 is equal to plus 1 in this way. At this time, the 3 decibel it is decreased. At point 2, it is increased by 7 decibel because we are using amplifier. At point 3, it is again reduced 3 decibel. So, it means 7 minus 3 and 7 minus 6, 1 decibel. This is. So, we can calculate it very easily. While if we are saying that 10 times or half times power is increased half, so it is not easy. That's why we can convert it into decibel. So, this is one of the reason. Okay. Sometime the decibel, the power, the unit decibel is used to measure digital power, signal power also in milliwatt. In this case, it's referred to the dBm, decibel in milliwatt, and it is calculated as decibel in milliwatt is equals to 10 log 10 Pm, where Pm is the power in milliwatt. If the question is like that, the power is given into milliwatt, then the calculate the power of signal in decibel in milliwatt is minus 30. We can calculate the power in the signal as dB is equal to 10 log 10 Pm is equal to minus 30 if it is given. Then 10 log 10 Pm is equal to minus 3. So, Pm is equal to 10 to the power minus 3 milliwatt. So, this is how we can calculate milliwatt also. Loss in the cable usually defined in decibel per kilometer. If the signal at the beginning of a cable with 0.3 decibel per kilometer, it has a power of 2 milliwatt. What is the power of signal at 5 kilometer? So, this is another example. So, the loss in the cable is 5 decibel, that is in decibel 5 multiplied by minus 0.3, it means it gives minus 1.5 decibel. So, we can calculate the power as dB is equals to 10 log 10 P2 upon P1, which gives minus 1.5. So, P2 upon P1 is equals to 10 to the power minus 1.5, or it gives 0.71. So, P2 is equal to 0.71 P1, or we can say 0.7 into 2, or that is 1.4 milliwatt. We can solve this particular question this way. Okay. So, this is all about the attenuation. Now comes on distortion. What is distortion? Distortion means the change in the shape of signal. This is the composite signal that is sent by the receiver, okay, at the center level. These are the signals in component phases, because if we talking about this signal, different types, so these are the different phases. So, at the receiver end, the signal received in this signal, received it. So, the shape has been changed drastically. What will happen in this case if the shape has been changed? So, if the shape has been changed, so it is very easy, it is not easy to recover the shape. But what can do? We can if we are able to measure these components out of these phases, then only we can recover the shape of the signal. Otherwise, once the shape of signal has been changed due to anything, due to any reason, it is not easy to recover it. Until unless if we have divided the component out of phase in this way. So, if these are, then we can receive the correct signal, otherwise the signal has lost its shape. Noise. Noise. वैसे आप लोगों को लगता होगा ना कि noise it means it disturb the signal, it change the shape, So it means it is distortion. If noise change the shape of signal, then it is distortion. No, noise is what? Noise is added to the existing signal. What is the existing signal? My voice is my voice is passing through to your ears. Another voice is also coming to ears. It means two voices are mixed or two voices has been added and reached to your ears. So it means noise is the parameter, is the thing that has been added to the transmitted channel or transmitted signal. So this is the transmitted signal. This is the noise. Noise has been added to the transmitted signal, and finally this we have received it. The shape has been changed? Yes. The power has been changed? Yes. The power can be increased or decreased? Yes. So it means noise is the combination of distortion and attenuation. Noise is the combination. The shape of signal can be changed, the power of signal can be changed. Increase or decrease, anything can be happened. So what can we do? We can minus, we can reduce, we can deduct the noise from the existing signal. Then only we can recover our exact voice what the sender has sent. Okay. So in this way, there are various numerical examples. You need to understand each and every example very closely, because these are the examples that is very important for your examination purpose. So SNR stands for signal to noise ratio. So the power of signal is 10 milliwatt and the power of noise is 1 microwatt. What is the value of SNR and SNR dB? Signal to noise ratio and signal to noise ratio in decibel if we are measuring in decibel also. So SNR is 10,000 microwatt upon 1 milliwatt is 10,000 SNR, while SNR dB is 10 log 10 is 10,000, which gives 40. So these are the formula, SNR and SNR dB. Keep in your mind that these are the formula. SNR, the formula of SNR dB is 10 log 10 SNR. SNR 10,000. So that's why SNR. This SNR is 10,000. 10,000 is what? 10 ye and 1 mu watt. So 10,000 mu watt upon 1 milliwatt is 10,000. Okay. So this is how you can calculate this one also. So value of SNR and SNR dB for a noiseless channel. If we are seeking is a noiseless channel, noiseless, where there is no noise, noisy नहीं है वहां पर, तो क्या होगा? अगर noisy नहीं है तो signal power, basically what is the formula of SNR? The formula of SNR is equals to signal power upon noise power. Noise power. Now, what is in this case? Signal power. What is the signal power is? But noise power. If the noise power becomes 0, then SNR is infinite. And also, SNR dB, it gives also infinite signal to noise ratio. So we cannot never achieve this ratio in the real time, as it is an ideal condition. There is no communication channel, there is no any medium of communication that is noiseless. Every communication medium has somehow some noise is also there. So we cannot say this. So two cases of SNR, a high SNR and the low SNR. We can see this. This is a large SNR cases, this is a small SNR cases. This is a noise, the signal noise and signal plus noise. In the high, it can disturb the peak and lower value only. But in low SNR, where there is a low SNR, it can disturb the shape of signal. So, this is the example where composite signals are there, so it can disturb it can edit to the higher and the lower one. Okay, this is a signal. Where in this case, the signal has been completely changed and the shape of this. So, large SNR is quite enough, but not enough. We have to reduce the noise from the existing signal. So, data rate limits. The very important consideration in the data communication is how fast we can send our data from one end to another end. That can be bits per second over the channel. So, data rate depends on the various factors, like the first factor is obviously the bandwidth available, how much bandwidth we have. Every communication channel had this capacity to transfer the data. Like for example, if we are saying that we are using the UTP Cat5 cable or Cat6 cable, Cat5 cable has the capacity to deliver the data as 100 Mbps, while Cat6 cable is able to deliver the data as 1 Gbps. Similarly, if you are using optical fiber cable, it can deliver data 1 Gbps also. So, the bandwidth available, the levels of signals we can use. जितने ज़्यादा levels होंगे, we can deliver the number of levels, number of bits per level is higher. But इसकी threshold होगा. Beyond the threshold, we cannot send multiple signals at a time. The quality of the channel, the levels of noise also. So, noise के लिए हम इसमें कुछ स्पेशल भी पढ़ेंगे. Increasing of noise, increasing the level of signal may reduce the reliability of signal. It is not reliable when we are sending multiple signals in a level. Multiple level signals. So there are two types of theorem is there, Nyquist and Shannon algorithm. Okay, so we will discuss this Nyquist and Shannon algorithm. Consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with two signal levels. The maximum bit rate can be calculated in this formula. The formula of this is equals to 2b log 2 L. This is a formula. 2 into bandwidth into log 2 L, यानी कि number of levels. It means if the question is this, the bandwidth is 3000, the bandwidth is 3000 Hertz transmitting a signal level with two signals, so L is 2 and the formula is putting here. So, this is the Nyquist theorem formula. Does the Nyquist theorem is the bit rate agree with the intuitive bit rate we described in the basement transmission? They match when they have only two levels, 0 and 1 only. Otherwise, in all other cases, it is not. The bit rate is 2 times the bandwidth if we use only the first harmonic in the worst scenario. However, in Nyquist formula is most general than what we have tried intuitively. It can be applied to the basement transmission or modulation. Also, it can be applied when we have two or more levels of signal also. So, this is the Nyquist formula. Consider the same noiseless channel. Keep in mind, there are two signals, there are four signals, the same. When we have only two levels, the bit rate is 6000 and we have four levels. There are four signal levels. This is 4. So, we have 12,000 BPS bits per second. So, bit rate is quite higher if we are increasing the level of double. So, bits per second 600 and this is 6000 and this is 12,000. Now, another thing is that if we need to send 256 kbps over a noiseless channel with a bandwidth of 20 kilohertz, how many signal level do we have to calculate? L. We need to find L level. So, this has been given, you need to calculate L. You can calculate L very easily. One thing is that if you are calculating L so L is to the power 6.625, which gives 98.7 levels, which is not feasible. Since the result is not in the power of 2, we need to either the increase of number of levels or reduce the bit rate. Okay. So, if there are 98.7 levels which is not feasible, either we have to treat it as a 128 level, या तो हम इसे 120 लेवल कर दें या इसको रिड्यूस कर दें, कुछ ना कुछ फार्मूला हमें लगाना पड़ेगा ना. So if we have 128 level, the bit rate is 280 kbps. If we have 64 levels, अगर हमने इसे reduce कर दिया 64 level, then a bit rate is 240 kbps. So what is good for us? What is good for us? Listen, if we are increasing the level, only 40 kbps is increased in the power bit rate, and we are decreasing only 40. So better is to use, better we keep only 64 levels in the bit rate is 240. So the correct answer is this one, not this one. Okay. So when you find the level in point or level is not correct, you need to calculate in this way. Consider extremely noise channel. Extremely noise, it means only the noise is transmitting. The noise has disturbed the signal and only noise is transmitting. With the signal to noise ratio is almost 0. Signal power is whatever, but noise power is too high. So that becomes 0. What is the capacity of this channel? B log 1 plus SNR, it means 0. So it means extremely high? No, never. We cannot use that particular extremely high noisy channel. We can calculate the theoretical highest bit rate of a regular telephone line. Yes, we can by this formula. 1 plus SNR, 3000 is bandwidth, SNR is 3132, 3162, which gives 3163, or we can say 34,860 VPS. It means the highest bit rate of the telephone line is 34.860 kbps. If we want to send that faster than this, we can either increase the bandwidth or improve the signal to noise ratio. How can we improve the signal to noise ratio? Increase the power of signal and or reduce the power of noise. Simple. Okay. So yes, for the practical purpose, when the SNR is too high, we assume that SNR plus 1 is exactly same as SNR, because its SNR is 5000 plus 1 is 5001 na. So better is to calculate the 5000 only. Okay. So in this case, the theoretical channel capacity can be simply defined as this one. For example, we can calculate the theoretical capacity of the previous example is this one only. Okay. So plus 1 is not necessary if the SNR is too high. So in this case, we have a channel bandwidth of 1 megahertz bandwidth. So the SNR for this channel is 63. SNR is given as 63. What is the appropriate bit rate per level, per and signal level? First, we have to use Shannon formula, and the upper limit is capacity is equal to B log 2 1 plus SNR, which gives 10 to the power 6 log 2 1 plus 63. It means log 64. How can you calculate it? 10 to the power 6 log 2 2 to the power 6. 2 to the 4 to the 8, 16, 32, 64. Yes. 6. So it means what is 6? Or you can say 10 to the power 6 into 6 into 1, because log 2 is 1. So 6 Mbps. Okay. The Shannon gives the 6 Mbps. The upper limit for better performance, if we choose something, the lower 4 Mbps. So if we choose lower Mbps, then we use Nyquist formula to find the number of signal levels. Okay. So L can be lower. So Shannon capacity gives the upper limit, while Nyquist tells us how many signal levels we need. Okay. So this is the last topic we will discuss, bandwidth, throughput and latency. So yes, the propagation time. If we are saying that, let's discuss is theoretically bandwidth, throughput, latency and bandwidth delay product. So bandwidth, a particular bandwidth a signal can carry, how much data it deliver in a watt second. Throughput, if we are sending thousands data and you are receiving 900 data, 900 MB data. It means throughput is 10% lower. Latency, the delay. If we are propagating the signal, we are converting the signal, there is some delay, some processing. It takes some time in delay. Also, the travel time is taking also the some time. So, this is the delay. Bandwidth delay product. Due to some bandwidth, it can also delay it. So, for this, we can say that this is the throughput. If we can calculate the throughput as 1200 frames per minute and 10,000 is its carry 10,000 frames, 10,000 bits. So 12,000 multiplied 10,000 upon 60 is equal to 2 Mbps. So this is how we can calculate this throughput of the particular channel. The channel capacity is 10 Mbps then. So this is the propagation time. If the distance between 2 points is 12,000 kilometer and the propagation speed is 2.4 into 10 to the power 8, 10 to the power 8 millisecond in a cable. So propagation time is 12,000 multiplied 1000 upon 2.4 into 10 to the power 8, which gives 50 millisecond. Okay, the propagation time, transmission time, we can calculate it very easily. So in the next case, we will discuss some more things in this. So for current, we have to stop it now. In the next lecture, we will discuss some more examples, some more technicality in this area. So thank you for now.